coming. So today you're pleased to have Johannes Carmesin from TU Freiburg. Yes, and he has most ambitious title of this seminar series, Open Problems in Graph Theory. Please.
Yeah, thank you very much, and welcome. So I remember back in 2013 when I wasn't even born, right, just at the beginning of my PhD, and St. Il was kind of giving this inspiring lecture in Hamburg, kind of packed with open problems and new ideas. So before I only knew graph minor theory, there were only two types of problems. So one was leftover stuff from the graph minor theorem, and the other type of problem was applications of the graph minor theorem. And usually it was fairly easy to see how it should go, but kind of doing all the computations and the details took a whole PhD for one of those applications. And then this was the first time when I heard about this idea that you could kind of go somewhere completely fresh and like vertex minors and cut rank and kind of build a graph minor theory there afresh. And at this time I thought, that's kind of where the future is, and I wanted to be able to do that. And so now we're here 10 years later, right? I mean, graph minor theory is in blossom again, and yes, and you're all part of it. And right, and there are lots of energetic researchers here, so let's talk about open problems. And the first thing I'd like to talk about is temporal graphs. So what is this? So think about the internet and put like a vertex at every web page. And then if there's a link from one web page to the other, then you would put an edge. And then if you look at kind of the internet, and then this changes over time, right? Because web pages get changed, some get deleted, or some web companies merge, and these web pages merge. And so you should not think about this as a static graph, but rather as a graph that kind of develops over time. And another example would be, if you take a road network and just see kind of how it changes over time. They build some new roads, they destroy some roads, and perhaps there's some crossings, and they merge these crossings, and then you could kind of see how kind of this graph develops over time. And another example is you kind of take your brain out of your head and have a look at it, and then there are kind of all these neurons, and you put a vertex at each of them, and then they kind of change connections over time. And it's believed that to really understand what's happening in these networks, you shouldn't really look at it at a static graph, but to understand the full behavior, you really have to understand it as a graph that changes over time. So it's kind of this additional dimension which you get from the time that kind of is important to study the behavior. Okay, this is kind of why in science people are interested about it. Right, so what does this mean for us, right? So what's the temporal graph? So just kind of just fix a vertex set, and then at each time step you would be allowed to add some edges or delete some edges, and then you could kind of see how this develops.
Do you add one by one, or do you add a bunch of them at the same time?
It doesn't really matter. We could just always do one more. However, if you think about kind of these things, what we had when you have web page, first they also want to merge, right? Perhaps there were lots of links before, and then you want to merge them. And also, if you kind of see what we want to do with it, it seems like the things. Okay, so if you're interested in planar graphs, right? Then you could study kind of which graphs embed in the plane with the subgraph relation. But obviously, it's a bad idea, and there would be infinitely many obstructions for planarity. But you want to close it nicely by planar duality, and then you get the minor relation. And so something similar will happen here. So there are some questions about temporal graphs that look kind of very complicated, but now if we kind of do it kind of with graph minors, then everything will get nicer. So let's now kind of see kind of how this works. So what's the definition? Right, so we say that a sequence, temporal sequence, G1 G2 all the way to Gn of graphs sequence of graphs is temporal if for any two graphs that are adjacent in the sequence, you have that one is the minor of the other. But you don't, I mean, it's not like monotone, it can go up and down, right? Sometimes the graphs get smaller, sometimes they get bigger, sometimes they get smaller again, right? So you pick the properties for every I and n. We have that the graph gi is a minor of the graph gi at 1, or the other way around. So that gi at 1 is a minor of gi. Right, so this is more general than this notion kind of that's commonly studied in literature where you fix the vertex set and just add or delete edges. Now we are also allowed to contract edges and do the inverse operation of this, so uncontract some edges. And so the vertex set is then allowed to change over time. Right, okay, so that's what we call a temporal sequence of graphs, and you kind of can think about it kind of time running from left to right, and then you can see how the graph changes. And now you can also do minors with temporal sequence of graphs. So what does it mean? So we have kind of two sequences. When is one a minor of the other, you just want that pointwise, and they would be minors of each other. So let's write this. And it just gives you the definition for sequence of the same length, but if they're different lengths, it's kind of very easy to kind of adjust this, but it's a bit technical to write down. So given G sequence from G1 all the way up to Gn, and H sequence of H1 up to Hn. We say G is a minor of H if, yes, and as I said, I only give you the definition, skip the definition if different lengths. I mean, it's kind of clear what you want to do, but I think it's not very insightful.
Yeah.
So, right, so they have the same length n, and then, yes, and you want that if for every I and n, we have that H, Gi is a minor of Hi.
Actually, it's not to extend this for different lengths. Because do you want to repeat the same elements arbitrarily, so that for some repetitions you want to have a minor relation, or?
Okay, so you have one temporal sequence. So let me draw it like this. And then you have like another one. Wait. Yes. No, wait. Okay. So this is the small one. Okay, and then on top of it, okay, so you have sequence. I don't know. H2 in there, and you have H3, H4, and then perhaps another one, H5. And now what you would do, you would fix some intervals, and then kind of in here. Okay, so now and the others would all have fingered intervals in this example, and then you would require that G1 is a minor of. So you would kind of
do
put
the intervals have to be monetary, or just?
I mean, they would be intervals in kind of 1 up to n,
Okay.
and you want to kind of then kind of contract kind of the whole interval onto that graph, so that this graph is a minor of all of those in the intervals, and then you would be allowed to collapse this interval to just a single graph.
So you have to have the same number of like up and down intervals, or?
I mean, okay, I mean, no, I mean, you don't have to, but I mean, whenever you have like contract kind of 5 edges one after the other, you could always collapse it to kind of just one contraction where you would do all 5 at once.
Mm.
So you could kind of have it that it always goes up and down, because if it twice goes down, then you could just go all the way down and it wouldn't really make a difference. But yeah, that's kind of one of these small modifications to those sequences. Okay, and now Okay, so now we have a definition of minor, so what we now want to do is study graph properties for these temporal sequences. And of course, if we want to do something like graph minus, probably the first thing that comes to mind is planarity, right? Because we all know that the graph minus structure theorem did really grow out of Grotowski's theorem, where we kind of wanted to understand planarity. Okay, so let me first give you an interesting example. Okay, and the silly definition of when one of these sequences is planar is just to say that all of those graphs should be planar, right? But here's kind of something more interesting. So consider the following example. And that's the first graph in our sequence. And now we minor it down to a graph with only 6 edges, so only the colored edges survive. For example, you could delete those edges and contract all the others. And now this is then a minor of the following graph. So now you kind of add a bunch more to the graph. Right, so this is kind of just a sequence of graphs, so that this is a minor of that, and this is the minor of that. And I mean, all graphs are obviously planar because we choose some plane embeddings. Okay, but what we would be interested in, okay, so what now happens if I have a plane embedding of a graph, then it induces a plane embedding on every minor. Right, so if I delete that edge, I could do this deletion within the embedding, and similarly if I do the contraction, then I could do the contractions in the embedding, so this embedding induces that embedding in this sense. And every embedding of a planar graph induces a unique embedding on every minor. And for example, this embedding does not induce that embedding, right? Because there you would want that kind of, at this vertex it would alternate between blue and red edges. And so what we'd want, and I will write down the formal definition in a second, is that along the sequence, I mean, we know that this graph is a minor, has this graph as a minor. We want to fix an embedding at each of those graphs such that if this is a bigger graph, this embedding induces the embedding on the smaller graph. Right? So this should be that the whole sequence is embedding, it should be compatible along these places where we take minors.
So I mean, here you have a graph with an edge coloring.
So just, I mean, every edge has a name, but I just
I see.
put some color so that
Labeled
it
graphs.
stuff that's important. And kind of it matters kind of, I mean, here you kind of, yeah,
Yeah.
it's important kind of what the names of the edges.
Do you have a concept of like, I mean, there's a distinction between plane graphs and planar graphs in graph theory typically, right? So anything isomorphic to the graphs embeddable on the plane is called planar. So do you also define like planar temporal graph where you can find such an embedding, or you fix an embedding?
Yes, so we call it simultaneously embeddable, so perhaps to avoid it.
So that's what you
Yes, but yeah, I will write down the formal definition now. So we say that a temporal sequence is simultaneously embeddable G1 up to Gn if there exists a sequence iota 1 all the way up to iota n, so that iota I is an embedding that, we have that for every I from 1 to n minus 1, we have that they are compatible. And what does compatible mean? It means that if gi is a minor of gi plus 1, then iota I at 1, so the embedding of the bigger graph, induces iota I. Right? So this bigger embedding induces a unique embedding on every minor, and we want that this embedding we picked on the i's graph is induced by the larger embedding. And just kind of the analog thing here for things the other way around. So if gi plus 1 is a minor of gi, then iota I induces iota I at 1.
The edge labels come with the graph or the embedding.
Yes, so this is a very important and subtle point. So whenever I write minor, then I'm not allowing isomorphisms. So I just kind of delete and contract edges.
Okay.
And this is a very excellent question, and there's a very subtle point. So if you also allow isomorphisms, then we can show that everything is NP complete I'm going to talk about, so that's probably not so interesting. And that's kind of why you just take this kind of here. So this motion of minor, we just delete and contract edges, but you wouldn't apply graph isomorphisms. Okay, so let's come back to this example. So what about this? Is this simultaneously embeddable or not? So we want to kind of, so these are just abstract graphs, right? So we want to fix a planar embedding in each of them, so that
It's
they,
no, right?
Hmm?
No?
no, yes, no is the right answer.
Otherwise,
Yeah.
otherwise you wouldn't use that.
Right, okay, so why can't it be embeddable? So if you look at this embedding, I mean, okay, look at this graph, and in every embedding of this graph, there would be this red edge in the middle that only has 2 red edges next to it, right? So if you look at kind of in the neighborhood around this vertex, this middle red edge, this, no matter how I embed, I mean, the only other embeddings would be if I kind of swap it around, still it would just always have 2 red edges next to it. So if we look in this embedding, then every red edge must have a blue edge next to it in every embedding. And what are the possible embeddings? We could just kind of swap the order of those and also kind of reflect it around. And this would be all the possible embedding this graph has. And so you see here every red edge is next to a blue edge, and here there exists a red edge that's only next to red edges. And so they can't then induce the same embedding on this guy. Right? So this would be an obstruction to simultaneous embeddability. Okay, so we know kind of there exists kind of these obstructions to simultaneous embeddability. So this is an analog. Probably I want you to think about this as kind of K5 is an obstruction to embeddability in the plane. This thing is now an obstruction to simultaneous embeddability. Then we have the following theorem. Yeah, so this was my PhD student Will Turner, and this started all as a master's project where I thought, yeah, well, you know, I like this kind of embedding 2 complexes in 3-dimensional space, so that's like 3-dimensional graph minus 0, so 1 additional dimension. And so here it's the same, right? It's just kind of graphs plus 1 dimension, so you should be able to kind of use these results to prove something about temporal graphs, but had then also some very bold conjecture, but it was false, and he disproved it, and that was his master's thesis. And now, 4 years later, you know, this I think very lovely theorem, and it was lots of work. I mean, I didn't expect that the problem was so hard, but he has lots of super exciting constructions, and yes, so now we have an algorithm. Okay, so yes, so first, right, so we would be interested now in this algorithmic problem, right? So someone gives you a temporal sequence, write a computer program that checks whether it's simultaneously embeddable. And there's the following fact, and this had been known for, I think 10 or 20 years before we started about thinking about those problems. I think they looked at a very different construction. So if you translate their results, and I should look up the names. No, I haven't. What? Okay, so this is bad. So I thought I had written them, but I can't find them. Okay, I looked them up later. I'll tell you. Okay, so the fact is that the simultaneous embeddability is NP hard for connected temporal sequences of connected graphs.
Embeddability into the plane or any other surfaces?
So we define simultaneous embeddability. So the embedding of GI here in the plane. I mean, yeah, of course. I mean, you could ask this for kind of arbitrary surfaces. I mean, this is kind of, yeah. I mean, there are lots of questions here. You already see that. Yes. So, I mean, if you're just interested in the problem where you even make all these graphs connected, it's NP hard. On the other hand, if you say, well, how about 3 connected graphs? But then it's very trivial. Because like 3 connected graphs have unique embeddings, right? So you just, each of these graphs, you kind of just take the unique embedding, I mean, up to reorientation, and then you start with the first graph, pick the unique embedding, and then you go here and also take unique embedding, and perhaps you reorient so that this embedding induces this embedding. And if it's not possible, well, you already have an obstruction, and then you just go along the sequence like this, easy linear time algorithm. So that's not, okay, so 3 connected is easy. 1 connected is NP hard. So really the interesting case is what happens if the sequence is 2 connected. Okay, and this is kind of what this is about. So for every temporal sequence of 2 connected graphs, so meaning all the graphs in the sequence are 2 connected. Graphs is simultaneously embeddable. Or there exists a sequence of something that we call improvements to an obstruction in one of 6 lists. And then the right, so okay, so this, okay, so I don't know, because it would be too much to say that this is like a Kuratowski's theorem for the simultaneous embeddability. But so what we have found 6 lists of obstructions, and this is kind of a special case in kind of one of those lists, kind of sequences that look like this. But they're kind of, yeah, and one other list is just that you have 3 connected graphs that kind of just don't match up, so that's kind of trivial and boring. But then there are kind of 4 other lists, kind of, yeah, so similar like this. And if you're in one of those lists, then you can't be simultaneously embeddable. And so what we can do is now we start with a temporal sequence, and then we have kind of this idea of improvement. So this is kind of one way to kind of make this temporal sequence smaller. And so either you're simultaneously embeddable, or you can make it a bit smaller until you can, and yeah, these improvements would be so that you're embeddable before, if and only if you're embeddable after. And you kind of iterate on this process, and either you eventually find that you're simultaneously embeddable, or you would find one of these 6 obstructions to embeddability.
Is the improvement via this minor?
Yeah, so this is what you really would hope, right? So it should be that you kind of, I mean, like in Kuratowski's theorem, it should be like you have this big sequence and just dually you play that minor down, minor down, minor down. And so this we couldn't do yet, or perhaps it's also not possible. So one of the difficulties we have is that kind of by doing these improvements, we had to go out of the class of graphs. So what we had to do is to add some additional data. So this is similar as you know probably from coloring, right? So perhaps you want to prove something by induction, and it doesn't quite work because coloring is not so nice with induction, right? And then you introduce this list coloring. And this works quite well with induction. And we had to do something similar here. So we had to kind of minor a bit down, and then we had to add some additional data to those things. And then we actually have these temporal sequences together with kind of a list at each of them. And so, and 2 of these obstructions, they kind of come with these lists. So I mean, I mean, we didn't expect this to happen, but you know, it happened, and so kind of there are 2 of those lists, obstructions with lists. Yeah, so they are a bit complicated, and I mean, I'm hoping it could be simplified, but it's already 70 pages, so we thought we're going to stop there and. And this is it. Yeah, because this theorem actually implies that you get a polynomial time algorithm for simultaneous embeddability. Simultaneous ability for 2 connected temporal sequences is infinite.
Yes. Do you measure the size of your instances? Is it the number of, like the length of the sequence times the size of the graphs or something?
I mean, okay, so it's a bit more complicated. So what you do is you look at all those graphs in the sequence, and then you compute the touch decomposition, and you count how many bags are in the touch decomposition. And then you also have to weight these. So kind of the first one gets like the biggest weight, and then it goes down 1 always in the sequence. And this is kind of how the size of the improvement is measured. And that's kind of the parameter you improve each step.
I meant just for polytime algorithm. What
Yes,
is the size of this? The size of the instance?
In the size of the input, yeah.
Okay.
Just the
All
union
of
of
this, yeah.
kind of disjoint union of all those graphs.
But your answer was like to how you measure the improvements, right?
Yeah.
Yes, so how you measure this improvement. Yes, and then kind of, if you look kind of back at these constructions where they had NP hardness results, also this then generalizes kind of lots of results in kind of this area with these sunflower CP problems and so on, but let's kind of not talk about this because I want to tell you some problems that are open. Right, so now, so I think what this shows you is that actually graph minor theory works for these temporal graphs. And now you could take your favorite theorem from graph minor theory and see, kind of try to find a temporal analog, right? I mean, it seems like every graph property, you would kind of get a very nice class and there would be obstructions and so on. So I mean, probably the most obvious thing you want to ask is what is with tree width, right? I mean, it's also, I mean, if you have a tree decomposition here and then here's a tree decomposition here, right? So you could also kind of do that, but that's probably difficult. But I think super exciting. So what about simultaneous tree width? Yes, but let's kind of do something more concrete. So something we have here in this theorem is that, and we have this assumption of 2 connectedness, and perhaps we could actually get kind of don't need any connectivity assumption if we kind of look at problems at smaller classes. So for example, what about outer planar graphs? Right? Could you perhaps get a polynomial time algorithm for outer planar graphs? Yes, okay, so let me first say what's the definition for outer planar? So it would say that the sequence G1 all the way up to Gn is simultaneously outer planar if the sequence of the cones of these graphs, so these graphs obtained by adding one vertex that is complete to everything, if the sequence of cones is simultaneously embeddable. And then, very natural open question is outer planarity simultaneous outer planarity in P? Simultaneous outer planarity. Yeah, I think if that was true, that would be super nice because you wouldn't have a connectivity assumption, right? So perhaps it's a bit too kind of much to, I don't know, I think it could be true. And so then perhaps you could also perhaps do the same with serials parallel, right? Perhaps think a bit kind of what would be the right kind of simultaneous notion for serials parallel, but you could really take your favorite graph property and see what's the simultaneous analog of this, and then you could kind of study kind of how you could build these sequences, what would be the obstructions, and then prove some excluded minus factorizations for this class. Yes, so this is the first area I wanted to talk about.
Do you have any expectation when you are only dealing with the maximal outer planar graphs? You are only dealing with the maximal outer planar graphs. So do you have any expectations?
What do you mean? If you want to restrict to maximum?
Yeah. So if we restrict to only maximal outer planar graphs, then do you have any expectation for that question? So
I mean, I'm hoping this is in P. So
yeah.
perhaps a bit bold, but you know.
Yeah.
I mean, that you only need one connectivity is clear, right? Because if you add this additional vertex, it gives you, then you could apply this result for two connected, right? So the question is, could you kind of go all the way?
So this NP hard reduction has lots of single vertex cuts, probably. I mean, if you have an arbitrary graph and you make it into a cone, then you're definitely connected, but you really have all of this.
But yeah, I mean, outer planar graphs are very special, right? So I don't know. Or perhaps you have to go even small. I mean, I don't know. So I think it would be nice to find like nice classes where you completely are kind of polynomial all the way. But also for more complicated things, perhaps like tree widths, we're going to need some connectivity assumption. I don't know what we're going to need. Or perhaps, yeah, I don't know. Yeah.
So I'm guessing, like, if you talk about tree width, you could ask for some sort of grid theories. But I would guess that there's something that like abstracts the simultaneousness, but not the tree width of the graphs. Do you have some intuition what this could look like? This is different.
No,
kind of abstraction?
but I could tell you that people told me that the brain is made up of 6 planar layers, right? So perhaps that's why kind of this tree width thing would be super interesting, right? Because you want to understand what's kind of the planar layer structure in the graph and how things change. So I think it's super important. I think this I can tell you, but I think I can't tell you more.
Okay.
Yes, okay, so let's kind of move to the next topic. So what's the next topic? So next I'd like to talk about connectivity augmentation. So what's this problem? So yeah, completely fresh topic, so you don't have to remember anything from what came before. So let's think about a graph as some electric network. I don't know, something like this, right? So this would be kind of the cables kind of connecting kind of various things you have. And some annoying thing, kind of when this vertex kind of doesn't work, right, then you can't kind of have electricity flowing from here to there, right? So then some politicians come and tell you, well, actually, you should build some new cables in such a way that this doesn't happen anymore, right? So you want to kind of guarantee that the graph has a certain connectivity. But you know, politicians don't have an infinite, or perhaps they have an infinite amount of money, but they don't give it to us. So they don't allow us to kind of just build a connection from kind of over here to over here, which would probably completely solve the problem. But they just have like some of the edges. Perhaps they allow us to kind of build an extra cable from here to here, or I don't know, perhaps one from here to here, perhaps one from here to there. And now the question is, given kind of all these different edges, you should pick a minimal amount of those edges so that actually you get, say, 2 connectors in this example. Right, so this is the connectivity augmentation problem. So let me write a bit more details. So the setup is you have G a graph, and you have L the set of non-edges of the graph, and they are called links. Right, so for example, this would be these 3 blue things here, and you're also given some positive integer k, and you're given some target connectivity lambda. And now the connectivity augmentation problem is can you find some subset of so some set of links, subset of L that is not too big, so it should have size at most k, so that if you add it to G, this is lambda connected. Right, so this is kind of this general version of the problem. Okay, so perhaps a few remarks about this. So if you just allow L to be all the non-edges, then this is kind of easily polynomially solvable and not so interesting. So now, right, but if you let this k be part of the input, then this gets NP hard. So then you really want to kind of look into this FPT version, where k is now a fixed parameter, and you want to know kind of, given this fixed parameter k, is there a polynomial time algorithm that selects the k best edges so that I get kind of my target connectivity lambda. And yeah, lambda is always fixed in this problem.
So lambda is fixed, and you want the complexity to depend on k? Or, I mean, you could be exponential in k if you want it to be polynomial.
Yes, so you would be interested in algorithms of with this running time. Any computable function in k times constant, possibly depending on lambda.
Yeah. Okay.
Yeah, so this is the target running time, and then you would say it has an FPT algorithm with fixed parameter k. And yeah, so this is the result from Marx and Bay that for connected graphs, so now you assume that G is connected, and lambda equal to 2. So you start with a connected graph and want to augment to a 2 connected graph, then this is FPT. And even with weights. And yeah, there were some earlier versions, but I think this is a very nice, clean paper where you can read this and they even do it with weights. But yeah, and there's also some other kind of earlier results on this, but so far, everything people could do is kind of doing one connectivity at a time. So go from 0 connected to 1 connected, or from connected to 2 connected. But yeah, so actually, so this is with Ramanujan and Sridharan. We now know that's true for lambda at most 4. And it's not a coincidence, kind of this 4 is not just some number and we kind of got tired after this, but actually we have kind of this, I mean, some of you know there's this angry theorem, and so this goes kind of all the way to 4, and this is very essential in this proof.
Are you assuming the graph G is connected?
No,
Ah, without.
we go from 0 to 4.
Weighted one or?
No, I mean the paper is already too long, but yeah. Yeah, so this was very funny. So I think, yeah, so actually Ramanujan invited me to give a talk in Warwick, and then before that, I mean, yes, then on the day just before the talk, he explained the problem to me, and then I gave a talk about this angry theorem, and then we realized that kind of the problem he asked me was kind of, I mean, the method from the talk kind of answered that problem, and I think it never happened to me before, and I think it never happened again, right? That you go somewhere for a talk, and they just think, well, that's an interesting problem, and I mean, I didn't submit abstract or so, right? I just went there and gave a talk, and he didn't know what it was about, and apparently the talk answered the problem. I mean, I don't know. Super crazy, yeah, but yeah. Yeah, this was a fun experience, but it's almost written the paper. Yes, okay, so, okay, that's all done. So what questions do we have there? So the first thing is, I mean, okay, this is connectivity augmentation, but perhaps we want do proper minor theory, right? So what's the minor question for this thing? So perhaps what you want to have is the following more general setup. So you have a graph G, which is a minor of a graph H, and you have a set L, which is a subset of the edges of H without the edges of G. Right? So for example, it could be that H is just a complete graph on the vertex set of G, right? Then you would just be kind of in this old setting. And then you question is, can you prove you solve connectivity augmentation? In this more general minor setting. And I think this is much more interesting than, for example, going to weights, because I think it's a very natural extension of subgraphs, right? Take minors. So why not? So wait, I should also say
I don't understand.
there's
the
something
problem.
missing. Yes. So so you want to pick. I had forgotten something here. Let me add this. So you want to know, is there some S subset of L with, of course, again, size of S is bounded, so that if you look at the graph L, but you only minor away, or minor 2, the edges in G together with S. Right? So you take this and you ask, is it lambda connected? I mean, when you have that G is a minor of H, there's kind of each way a specified way whether you want to contract or delete it. And now
so by G, you take some minor model of G and then take the edges of G in that minor model? Oh, so
yes,
I don't understand
yeah.
what you mean by E of H minus E of G. So when
a
you
minor
take,
2. So wait.
when you say L is a subset of the
On the left hand side. L.
So that so yes, this, thank you very much. So this should be H. Oh, sorry. So you take the graph H, so the big one, and you want to minor in the direction of G, but you don't minor those edges that you picked, right? So you pick the set S, and those you don't minor away, but all the others. For example, if this is just a complete graph on this vertex set, then you would just delete all the edges except for those in G, and these additional edges in the set S. But now for each edge, it's specified whether you want to delete it or contract it. Yes, I think we should. Okay, so let's first have a quick example. So this graph is a minor of that graph, right? And you would you would kind of contract this edge, right? You would contract E. Yeah, perhaps we should also have some other edges here, which you don't want to pick. And now, actually, there's a set S of size 1, so that this thing gets 2 connected. Right? You want to pick this edge E, and if you contract everything except for E, then you get this graph. I mean, these were all marked as delete.
Oh, so in some sense you prevent the edges in S not to be contracted,
Yeah.
not to be deleted.
Yes.
I see. So you want to select the most K edges so that you don't want to apply any operations.
Yeah. I think it's a very natural extension of connectivity augmentation, which is very well studied in computer science, to our minor setting, right? So I think it seems like our graph minus method should also be possible in this sense. I mean, I think it's very plausible. I have no clue how it works, but I think it's an interesting problem. And and nobody has worked on it before, so that's also good. I mean, I don't know. You don't want. I mean, it depends, right? But perhaps as a very young person or PhD student, you don't want to work on those problems that already 20 people thought about before and couldn't do it, right? So perhaps the first problem you work on should be something where nobody has thought about it before, and you could kind of explore lots of things.
We have a lot of students here, so.
Yes, and there's
There's one more board. Oh no,
I think there was half a board, right? And also what I find quite striking about this connectivity augmentation is that the edge version is not known. And this I find quite surprising, because with vertex connectivity you really reach the bottleneck of 4, and we would need a better decomposition of 4 connected graphs to kind of go for the next step. But for edge connectivity there are kind of much stronger decomposition methods. So you don't have this barrier at all. So I would be surprised if it wasn't possible to prove it for edge connectivity, the whole thing. I think it should be possible. But yeah, I didn't think about it. But yeah, I think it's a good problem. So I should stop now, right? So I have 50 minutes? And so
I mean, okay, if you want to say a little bit more, it's okay. So 60 minutes, it's 50 to 60.
Well, it's 50 minutes now, right? And it should not
you can
rush
start if
for
you
the
want.
next problem. Yeah, I think probably I would finish then here. Yeah, so thank you very much for listening.
Thank you. Any questions? Or solutions?
Big problem for listening them.
So for the connectivity augmentation, do people thought about matroid pattern? When you go to the cycle matroid, does it make sense to think?
Yes, I mean, it totally makes sense. I mean, so far for graphs, they knew barely anything, right? They could just go one connectivity at a time. But I mean, also the rank version with cut rank, right, for connectivity augmentation, I think is very interesting. And I think it's all in reach now, and there are kind of lots of, I mean, that's why I mentioned it, right? So it's, I think both of these areas are something where there are so many problems now, we could basically I mean, not just look at the problems I presented, but they kind of, I think lots of things that are open now.
So regarding the simultaneous tree width, what do you think is the, like, what would be the kind of a test questions to see if it is the right definition or bad definition?
For simultaneous tree width.
Yeah.
Okay, so I mean, you want to fix the tree decomposition. Probably the notion could be, right, you want to fix the tree decomposition for each graph, and you have the property whenever I have a big graph and I take a minor, then I can do the minor within the tree decomposition, right? If I delete an edge, or if I contract an edge, I mean, so then you could, and then you would know what a simultaneous tree decomposition is, and now then you could study simultaneous tree width, which would just be kind of minimum simultaneous tree width, and yes, I think that's the obvious thing to try, and then you're gonna have to see what happens. But yeah, probably I would start kind of somewhere smaller, right? So just, I don't know, do widths at most 2 or 3, and then
For your theorem for simultaneous embedding, I mean, this is a silly question, but does it imply Grotowski theorem?
in a very trivial way, because we have one of those obstructions
Yeah.
that looks like this. So the list of length 1, which is K5.
Okay.
And also we have the list of length 1, which is KC3.
Yeah.
So yes, they just come up as obstructions, and so of course we have to use it. And so yes, that's why it implies it.
Any other questions? If not, let's thank the speaker again.